I'm Mariana Pimenta, and I'm a master's student at the University of São Paulo, Brazil. I'll be presenting our work titled Light Touch Increases Muscle Synergy Coordination, Reducing Synergy Space in Quiet Bipedal Stance. I'll begin with an introduction, then I'll talk about the methodology used for data acquisition and processing. Then I'll present the results, and finally I'll summarize our conclusions. So muscle synergies are specific muscle groups activated in coordination by the central nervous system, and they're used for achieving different behaviors or tasks. So they can be modeled as the composition of the data in muscle activation in matrix M and to a matrix W of activation weights and a matrix C of neural commands in time. So neural commands given by the central nervous system will activate in time each muscle synergy that represents a weight for the specific muscles. So every muscle has its weight on a synergy. And for this extraction, usually we can use electromyography data, and we'll be using the non-negative matrix factorization algorithm for the decomposition. So some open questions still are how the central nervous system selects specific synergies for a particular behavior. And our goal is to shed some light into some strategies that may be used specifically in standing posture. We'll be studying quiet standing. So despite the name quiet standing, it's not completely static, and the body presents oscillatory and random movements, for example, forward and back. And there have already been proven that muscle synergies exist in this context, and usually they are represented by groups of muscles that have similar effects on the body, such as forward pushes or backward pushes. And we propose that these synergies may be different across different experimental conditions. So here we'll be studying the introduction of an unstable surface and also the additional sensory cue given by a light touch of the fingertip on a stable surface. So for this experiment, we used 16 healthy subjects in quiet standing, and we acquired data from 22 pairs of bipolar electrodes, from 11 pairs of 11 muscles from the right and 11 muscles from the left sides of the body, mainly in the calf, thighs, abdominals, back, and neck. And for the pre-processing steps, we can summarize here on the right, mainly in amplification, filtering, and normalization steps. And after this processing, we use the non-negative matrix factorization algorithm for the decomposition into matrices W and C. So as the name suggests, its objective is to provide always positive components. So it uses a multiplicative algorithm to update matrices W and C. And NNMF is usually used as a dimensionality reduction algorithm, and for this purpose we need to provide the number of factors that would be wanted. So matrix W would be 3 synergies in this case, because we determined that the variance accounted for all the synergies must represent at least 90% of the matrix M. So also we used some important parameters for evaluation of the outcome of the synergies, and they're named Synergy Stability Index and Synergy Coordination Index, where the Synergy Stability Index represents the similarity between a given synergy in a specific experiment and its repetitions, and the Synergy Coordination Index represents the coordination and between the different synergies 1, 2, and 3 for a specific task, and its vector product. So it represents also the synergy space represented by the synergies together. So the results are here given for a specific subject, representative subject, and we can notice that For synergies 1, 2, and 3, the results were quite similar across conditions. The conditions are here represented on the lines. So condition 1 would be the natural posture with a stable surface and no light touch. Condition 2 is with the addition of light touch. And we can see here on the left that the synergy stability index has increased a little bit. And for the condition 3 would be condition with this unstable surface and no light touch. And we can see that the stability index has decreased. So, however, we have not noticed significant difference between synergies found for each condition, and usually they represent, as we talked before, similar um, muscles with similar effects on the body. So, for example, the calf muscles that work together, or the abdominals and neck muscles. And here we'll see the results for the indexes. So on the top left, we see the synergy similarity stability index for with and without light touch. With light touch would be the red color. And in average, the synergy stability has increased with light touch. On the bottom left, the synergy coordination index has in average increased for light touch. And on the right, we'll see the results for the unstable surface. So for the stability index, the unstable surface, which is the red color, has once again increased the stability. But in the bottom right, we'll see that the synergy coordination index has decreased with the unstable surface. So to summarize our conclusions, the central nervous system tends to use some synergies, which are groups of muscles with similar functions together when it's trying to stabilize posture. So we haven't seen significant differences in the shapes of synergy vectors across conditions. However, we have seen a difference on the similarity between the synergies when using the synergy stability index and the synergy coordination index. Namely, light touch increases both SSI and SCI, while the foam pad or the unstable surface increases the stability index but decreases coordination between the synergies. These results have been specifically strong in subjects with higher stability indexes above 0.8, and light touch in this case always increases the coordination index while the unstable surface always decreases it. So we have concluded that light touch increases the synergy coordination index, reducing the synergy space, while an unstable surface usually reduces the coordination index, increasing the synergy space accounted for. So we would like to acknowledge our fellowships given by the National Council for Scientific and Technological Development and the São Paulo Research Foundation. And I would like to thank everyone for their attention and the International Conference on Biomedical Engineering and Medical Science for the opportunity. Thank you very much.